All right, so let's look at this is exercise 4 from section 3.5. So looking at some related race problems. So kind of akin to the optimization section. It's usually a good idea to start off by really getting a sense of the situation and that will often include drawing a picture. So I have a sailboat sitting at rest near its dock, a rope attached to the bow of the boat, drawn over a pulley that stands on a post. Okay, so I'm not even going to try to draw a sailboat. Here's my sailboat, just like that. So again, these pictures don't need to be good or representative of what's going on. They just need to help you organize. So a rope attached to the bow of the boat is drawn in over a pulley that stands on a post that is 5 feet higher than the bow. Okay, so 5 feet. So this is a rope that is directly vertical. Okay, if the rope is being pulled at a rate of 2 feet per second, how fast is the boat approaching the dock and the length of the rope from the bow to pulley is 13? Okay, so here's the boat. Dock is out here somewhere. All right, so we have a pulley is directly above the boat. Oh no, that doesn't make any sense. Okay. So there's a pulley up here. And this connects to the boat. So I think, let me just read through this again. Just a little bit hard to parse, but let's make sure. Sailboat is sitting at rest near the dock. A rope is attached to the bow of the boat. Oh, sorry, a rope attached to the bow of the boat is drawn over a pulley that stands on a post at the end of the dock that is 5 feet higher than the bow. Okay, so this 5 feet actually needs to be here. If the rope is being pulled in, if the rope is being pulled in at a rate of 2 feet per second, how fast is the boat approaching the dock? Okay, so I think we have a good situation here. It looks like we have a situation we can model with a right triangle. So now let's ask ourselves, what are the variables at play here? So I have a right triangle. Let's just label all the sides. So I have a sense we're going to set up Pythagorean theorems. Let's just call these things A, B, and C. So anything else we have to look at? A rope? Yeah, that should be it. So we have A, which stands for the distance from dock to boat. And what is that measured in? That is measured in feet. We have B, the distance from dock to pulley, also feet. And C, the distance from boat to pulley, also in feet. Okay. So now I can write an equation here. So I've already kind of decided this is going to be a right triangle. But before I write that equation for the Pythagorean theorem, let's make sure that's actually what we care about. If the rope is being pulled in at a rate of 2 feet per second, how fast is the boat approaching the dock? Okay. How fast is the boat approaching the dock? That sounds to me like we're dealing with like what we want to find out about is a rate of change, and specifically is the rate of change of one of these three distances with respect to time. So we want to know how fast the boat is approaching the dock. So that sounds to me like that's distance A. So I want to find a rate of change of A with respect to T. So I'm going to make a note for myself that dA dt, that's our unknown. That's the thing we want to find out about. So that's kind of like our finish line. How do we get there? So I'm going to write my equation here. A squared plus B squared equals C squared. That comes directly from Pythagorean theorem. So there is no involvement of time here. There are no rates here. So how do I make that happen? So I'm going to differentiate both sides of this equation with respect to time, which is something we can do even though there's no time involvement with any of these other variables here. So this involves some things you've learned from implicit differentiation, as well as things we've done with chain rule. So what is the derivative of a squared with respect to t? Well, first I have to differentiate a squared with respect to a. That becomes 2a. And then I have to differentiate a with respect to t, so that's dA dt. Very similar structure for b squared, so 2b dB dt equals 2c dC dt. All right, so knowing that we want to solve for dA dt, we better know everything else. So what is A? A is the distance from the boat to the dock at this instant in time. That does not look like it's a thing that I am told, but we have enough information to get there. So what do we know? Let me draw another triangle off to the side here. So we are being asked about the situation at a moment in time. At that moment in time, it says the length of the rope from bow to pulley, which is what? That's C for us. That's 13 feet. And we also know this B is a constant 5 feet. The pulley's not moving, the dock's not moving. So we can assume that 5 feet, that vertical height, is always true. So given two sides of a right triangle, I can find what the missing side is. A squared plus 5 squared equals 13 squared. A squared plus 25 equals 169. A squared equals 144. A equals 12. So let's start filling things in. 2 times 12 feet. dAdt is not something we know. That's the thing we were asked to find out. Plus 2 times B. B is a constant 5 feet. One thing that is different from the videos you're showing is that I am treating everything as a variable for quite a while. Whereas in the videos, I think at least one of the instructors, tried to figure out like what of these quantities are going to be constant. But I'm going to do that now. So yeah, there's no reason you have to do that early. But now we know that d, that distance doesn't change. So what does that mean about the derivative dB dt? Derivative is 0. Then equals 2c. C is the distance from the boat to the pulley. Do we know that here? Yeah, we're told that distance is 13 feet. Then dC dt is the rate of change of that distance. Do we know that? I believe we do. That should be, and we got to be careful here. I think that's going to be -2 feet per second. Why is it negative? Well, I am pulling in that rope, so I believe the distance is decreasing. The length is decreasing, so I'm going to call it a negative value, which should make sense because I think now we're going to get a negative value for dA, which hopefully you expect. So this middle term vanishes. So now I get 24 feet dA dt equals negative 52. I guess feet squared per second. Kind of strange units, but it'll all come out in the wash because dAdt is equal to negative 52 feet squared per second divided by 24 feet. So the unit is going to come out to be feet per second, which is what we would expect. 52 over 24. Let's find out what that is. Okay. I get a value of negative 2.17 feet per second. All right, moving on.